All right, pace of speciation. Guys, speciation could happen super fast or it could happen super slow. It's not just Darwin always considered it to be slowly over time, all of these accumulated changes, but it turns out that's not necessarily always the case. On the pace of speciation, we've got the gradualism module, and we've got punctuated equilibrium. The other model is called punctuated equilibrium. And this is what we tend to see in the fossil record. A long, long, long time of not much change. They are squat, 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 squat. And then suddenly, in the records, you see a big change. It goes from being squat to really long, really fast. Now, what might cause that to occur? What might cause a sudden change in a population from one look to another? In your mind, what could cause, now that I just explained to you what causes thin or small shells versus long shells, what happened right here at that rapid change point? Say it again? Sure. Suddenly, you're not in moving water. Maybe a bay formed. Maybe they got stuck in a lake. Who knows? But suddenly, there was a rapid environmental change that altered what was advantageous in the environment. You guys ran experiments with microevolution. You saw that very quickly in a short amount of time, if you have strong selective pressure, you get big changes in allelic frequencies. And that's what's happening here in punctuated equilibrium. Now, that's not saying only one of these theories works. Both theories hold and both theories work over time. It's just how are you going to describe any given type of change? So we have gradualism, we got equilibrium. There are a few factors that impact how quickly alleles change, how quickly evolution occurs. This, by the way, is a picture of a frilled shark. It has not changed since well before the dinosaurs walked the earth. Allopatry can increase the rate of evolution. If suddenly you have a geographic barrier that arises splitting two populations, the smaller the isolated population, the faster the evolution. Similarly, if you have high levels of natural selection, that is, there's a selective pressure that is pushing certain groups of organisms not to survive, you're going to see quick changes in the allelic frequencies. High mutation rate. The higher your mutation rate, the more new alleles are popping up. The more new alleles pop up, they're going to be acted on by the environment. So you get more options, and as the environment is selecting for one of those alleles heavily, you're going to see that allelic frequency rate rise. And then finally, generation time. Organisms with a short generation time, say bacteria that can produce new offspring within a few hours, are going to evolve much faster than an elephant would, or tortoise. Tortoise becomes sexually is able to mate. Sorry, for some reason the word is leaving me. Sexually mature, that's what it is. At about 40 years old. Their generation time is so much longer that they don't have the ability to have new alleles introduced into the environment due to, say, mutation. Their alleles are very slowly changing compared to that of a bacteria. Now I'm required to talk to you about evolutionary developmental biology. Now the deal is, there used to be this idea, and this is a wrong idea. I want to tell you right now, this is completely factually incorrect. But it was taught up until the 2000s that organisms could be classified based on their structures as they develop. So if you look at this is a fish, salamander, tortoises, chicks, hogs, calves, rabbits, and humans. At first, they all look sort of similar. They got these sort of big-looking noses. That's going to end up being their face, an eye, and a long tail. Developmentally, they all look about the same to begin with. But over time, their development, so here's the next phase of development. You see the fish and the salamander? They look sort of similar compared to all the rest that look alike. So we were able to say, cool, fish and salamander are more closely related. Come down to the next level, and you can say fish and salamanders look similar, tortoises and chicks look similar, and then hogs, calves, rabbits, and humans all look similar. Thus, we're able to say fish and salamander are more closely related to each other, tortoises and chicks are closely related to each other, and hogs, calves, and rabbits and humans are. That was the original idea behind evolutionary developmental biology. You look at their development, and you can start classifying them. But the deal doesn't hold true. What modern evolutionary developmental biology tells us, or talks about, is how are genes impacted by development? Remember, genes produce a certain phenotype. At some point in your lives, in your development, you were as a fetus, all of your fingers were connected together. There was webbing between them all. Just like here, there's webbing on a duck's foot. There's no webbing on a chicken's foot. During development, you had a gene that clicked on that sliced those webs. The duck has those same genes click on. I'm sorry, the chicken had those same genes click on. The duck didn't. Because of those differences in genes being expressed, you have two distinct species. They are very, very similar aside from that developmental step. This leads to, in humans, and a few other organisms, what's called heterochrony. That is, a relative difference in the growth rate of different parts of the body. Kids, when they're born, have proportionally gigantic heads. You've seen them, right? All these kindergartners running around, looks like their heads are gigantic compared to their little bodies. As you age, the rest of your body grows at a different rate than your head did. And thus you end up with what we would consider a normal-looking head, some of you. Different parts of the body growing at different rates is heterochrony. The other, you could think of juvenile characteristics could be retained, and that could lead to a new species. That's called paedomorphosis. Paedomorphosis is where the adult of a population retains juvenile characteristics of the younger form. The axolotl retains the juvenile form of its the salamander. It keeps its gills. Normally, a salamander will lose those gills, but not the axolotl. Do you guys know that these are functionally extinct in nature? Yeah, they're gone. There was only one. They evolved in one lake in Mexico, and they've literally paved over that lake and put in a parking lot. The good news is they're functionally extinct in nature, but they are not extinct because they exist in the aquarium trade in such high quantities. So they haven't disappeared from the earth, just from where they used to live. It is unlikely that they will be reintroduced. Because once you reintroduce them, then you're introducing a new species. Because their original habitat's just gone. So we've got panomorphous, which is just retaining those juvenile traits. It would be as if you some small child continued to grow and their head got big, got large as they continue to grow, which would look weird or sort of like a little gray alien type thing going on.